Now I'm going to talk for another 20 minutes or so on protecting groups, and I wanted to talk a little more about reduction. Again, I could just go for hours on this stuff because we have so many reactions, okay? Please go over all the videos. But anyway, so I'm still doing the review for the exam. Part 2. You know, please pay attention to all the synthesis problems I do this week because they probably will be relevant. I would recommend studying longer for this test because there's a lot of reactions. Anyway, okay, what I wanted to talk a little bit about was protecting groups and when you need to use them. You guys really only have 2 protecting groups, okay? You have a protecting group for a carbonyl, and you have a protecting group for an alcohol, and that's it. That's your whole repertoire. Okay, so you have this protecting group that if you add alcohol, it could be, you also could use like a ring, like a diol, or 2 equivalents of an alcohol. You can make an acetal or a ketal, and we have talked about, and you add acid to this. You would make like this. Realize it doesn't have to be linked. A lot of times people think it has to be a linked. It has to be a linked alcohol, okay? Or in the bottom case, you would make this, which you've all seen. And we've seen it again in some of our work in class, okay? That's a good protecting group in a couple of situations. Realize it can work the other way. In other words, you could use this to protect these. Okay, I'll show you what I mean by that. So you can use these to protect a carbonyl, or you can use that. You can use this to protect alcohols. Okay, your other protecting group is, which I did very rapidly in class. I said I'm just giving you this as a gift, a synthetic gift, right? So we talked about how the silicon is such a big atom that it doesn't have the substitution issues. I think we use silicon chloride. It doesn't have the substitution problems that other carbon-based species would have. And so you're adding like triethylamine or maybe pyridine as your proton scavenger. And what happens here is this essentially just goes in and kicks that out. Again, the silicon is so big that there's actually a lot of space between the methyl groups. And I want you to think about that a little bit. So you don't have the steric problems that you would have on a normal tertiary. And so it substitutes for that. The pyridine picks up that H, and then you end up with R, O, silicon, methyl, methyl, methyl. This is a good protecting group for alcohols. Okay, and I'm just going to give you some scenarios where you would use it. All protecting groups come off under different conditions. Okay, so, you know, the definition of a protecting group, which I will just say verbally here to save time, is a group that you put on under one set of conditions to block sort of a vulnerable or susceptible group so that you can do some other chemistry that would otherwise interfere with that group. And then you're able to take that group off under other conditions. They have to come off under different conditions. So this group, like for example, if you had this, etc., this comes off with acid, but not in the presence of alcohol. When you flood it with alcohol, it goes on. When you flood it with water, it comes off. In this context, I want you to be more aware of this as a protecting group, not so much mechanistically. I'm not going to ask you the mechanism of this. Now this one, I suppose I might, but if you had the alcohol protecting group, you know, this one that's already on, I'll have it on already. Most people in class, when I did this, I remember recognized it was just kind of it was sort of like just like a substitution reaction. That's how you should look at it. Now, okay, how does it come off? It's kind of weird. You take it off with, I'm having like a little brain spasm right here. I think it's ammonium fluoride you take it off with. And what happens, and as somebody, I remember somebody said in class, oh, the fluoride must come in and knock this out, and then you use the ammonium to protonate that. Okay, so I'll try to save a little time here. The ammonium would protonate that. Okay, you have to be responsible for some things like that. You're getting the rhythm of this a little bit. All right, so that's how you would take it off, and then your outcome would be your alcohol would be free again. All right, why do we need these protected groups? because we're working with these really strong bases like Grignards, organolithiums, and hydride reagents, and even Wittigs, okay, cannot survive. Carbonyls cannot survive under conditions where you're making Wittigs or Grignards, okay? So one example I gave in class, so the thing would be protecting groups. When would you use them? So there was this great example, two great examples in class. One was this. I said, if you had something like this is kind of like the classic example. If you had something like this, I don't know why I keep using an aromatic. I don't have to use an aromatic. Maybe just make it look a little different. But if you had something like that, and you were saying, oh, I'm going to make a Grignard reagent, right? And remember, Grignards have to be made in ether. I'm going to make a Grignard reagent out of this. Then, in a second step, I'm going to have this react with some ketone. Okay? That's not going to work. Okay? The reason it's not going to work is this already has a carbonyl in it. So you would have to change your strategy, and you would have to protect that carbonyl. So you'd say, okay, I want to do this sequence, but it's not going to work. So what I would do instead, synthetically, is I'd make an acetal. So I might go like, let's use the classic one. Okay, realize this is just horrible looking here. Let me fix this. It's still horrible looking. But this will make, so then you say, okay, I block this. All right, you block it like that. Then you would continue on your merry way, and you'd say, okay, I'll make my Grignard. I'm not going over a Grignard mechanism because we've done it a bunch of times. So pop in if you don't get it. But you reverse the polarity. Okay? And what this does, right, is this makes this delta plus. Now think about this. Had we not blocked that, this could easily have attacked that. All right? Then, in the next step, right, what would we do? Then we would add our carbonyl compound, whatever that was. I don't remember. It looks something like that. This will attack here. This will open up. So you'll have elaborated your chain. I hope I have the right number of carbons there. Okay. All right, this is very quick. You would do this, and then, okay, you'd add acid to it. Now, this thing's still protected over here, okay? Now, realize this gets protonated, and this will come off if you add H3O+, okay? So then when it comes off, what will you have, right? I'm sorry, I'm going in circles here. But you'll have, I hope my carbons are right. This will get protonated. A lot of people have asked me this. And then this will go back to the carbonyl because those are the conditions under which it comes off. Okay? So that's like the basic idea behind it. But realize you could use this in different ways. For example, okay, Wittigs, you know, that paper I gave you on progesterone, they had used it in a Wittig. So for example, like supposing I have something like this, like I just have that, and I want to convert that into a Wittig reagent and do a Wittig reaction, okay? I would have a problem because if I make a carbanion here, this could attack other molecules like itself. If not intramolecularly, it could attack. So similarly, I would protect it. Now realize you don't have to use the cyclic one, but I could take this, and if I did this, I'd have this. Okay, and then once I had it protected, I could start working on the Wittig. So I'd say, okay, then I'd add my P. Remember the Wittig, remember how to make the Wittig. This is a good review. That's a substitution reaction. Second, you've got to add N-butyllithium to pull the proton off. And then third, and after doing that, you will have a Wittig reagent, which will look like this. Okay. Go over that. I went over that in class, but go over it again. So this will be negative. This will be the phosphorus group here, plus, right? And then you would react this with some other carbonyl. Remember this reaction, okay? Makes that little box, the box collapses. But the thing is, if you think about it, if this group, if you had not protected this, when you get the Wittig, if you could get the Wittig, I don't think you could get the Wittig because this lithium reagent would attack the carbonyl too. It just wouldn't make it. So instead you block it, you do the chemistry, and so ultimately what I'm going to end up with here synthetically is I'm going to have a double bond to this thing, to this piece here. Go over that. That's a good thing to go over. And then if I follow this up with some acid, right, this is going to come off and it'll go back to the carbonyl state. You have to do it carefully. And again, if you look at that paper we did, look, they actually did that. How else could you use this protecting group? Okay? Well, you can work it the other way. Like supposing, this is a little nutty, but supposing you had some molecule that had two OHs in it. Now this is something I think is very important to reiterate, is that if I tried to do a Grignard, I'll keep it pretty simple here because it is a review. If I was trying to do some kind of Grignard and I had a Grignard reagent and I wanted it to attack here for some reason, you know, and I was just going to follow that up with some acid. The problem is, this is extremely important. These things go after protons so easily, it's not funny. They will rip a proton off of any oxygen before they will hit a carbonyl. So what will happen is this will come over and rip one of these off, or it could rip that one off. Okay, and that would destroy your Grignard reagent because then you'd end up with this. This is very important. I think sometimes people do not understand this, that this, like when I took the pyridine and took a carbonyl, took a proton off a carboxylic acid, that was legitimate because a carboxylic acid is sort of acidic. Pyridine isn't that basic. On the other hand, a Grignard reagent is super base. It is super base. It'll pull the proton off anything to the right of it on that table that I gave you. So they're very indiscriminate, and you have to protect things to use them. You have to like set things up so it goes exactly where it's supposed to go. So this would be a problem. But interestingly, what you could do, this is like a strategy you could take. You could say, well, I got these two H's. Why don't I just make, I don't know if this is going to work properly. It might work. You know, why don't I just make a ketal here? So perhaps if you added this, you might have some trouble with some cross reaction there. You might have to do a double protection. But let's say this, you could, I'm just saying in principle, or let's say we're doing a Wittig, that might be a better, you can have OHs around. But the thing is, the point I'm trying to make is that people frequently take, I don't think I have the best example here. People frequently take double, like say you're doing a hydride reduction or something like that. Okay? But the thing is, they'll take this sort of thing and protect it. You can protect it the reverse way, like that. You could start out, it could start out, like say it's down in the alcohol state. You could protect, I'm still having problems here. But let's say it's in some other state. You could protect this ahead of time before you even have the aldehyde or the ketone. You'd have to plan it out right. But my point is, you can protect two alcohols with this also, working the reverse way. All right? I'd have to come up with the perfect scenario for you with the number of reactions that you know. The problem I was worrying about there was that this carbonyl could also probably form an acetal with the alcohol. All right, and then the more classic case is the silicon. So supposing you had this. All right, and again, I'm just going to do an organolithium. So say you've got N-butyl lithium and you've got second step acid. This is not going to work. I can't emphasize this enough. This is going to come over and pull the proton off there. Accept that. That's what's going to happen. It's not going to attack the carbonyl. You have to have very, very open eyes when you're doing these reactions. Now, if you do all my flashcards, you'll run into all these scenarios, okay? You really will. So you would get this again. I think this is probably a better example than the last one I was doing. Okay, so you get that, and you'd have a lithium salt. And you'd say, well, goodbye, organolithium, because my organolithium is now pentane, and it has blown out the hood maybe, or it's sitting in your solution. Pentane's a liquid, so it would sit in your solution. Okay, so you say, well, that's no good. I've got to protect that alcohol. Well, probably a better way for you guys to protect alcohols is the method I just showed you. So instead of doing this, you'd say, I'll give that a little chirality. You'd say 1 chloro trimethyl silyl chloride in some kind of a base, like you could use pyridine. It has to be like a tertiary base or pyridine, so it doesn't want to connect to anything. 2, then you would add your N-butyl lithium. Think about this. 3, then you can take your, you can protonate this. 4, then you can take your protecting group off. This sequence will lead intermittently to this species. There will be no change in stereochemistry. Okay, you'll have that. Then the lithium reagent will, I'll draw it the way you guys frequently do, which is okay.